And so, let's see. What did we look at? We looked at integral of 4x cosine x. And we said, is this undoing the chain rule? That's always the first question you ask. It's the most prevalent technique that we're going to see is undoing the chain rule. So you always ask, is it undoing the chain rule? And we compare these two and we say no. If this were cosine x squared, then yeah, we would be undoing the chain rule because we've got essentially got its derivative over here. But with cosine x and 4x, it does not qualify for undoing the chain rule, so we did undoing the product rule. And then we looked at x squared e to the 3x. And likewise, the first question we ask is it undoing the chain rule? And we said no. In order for it to be undoing the chain rule, this power would have to be what? What power do we need on this x here? 3 cubed, right? So we would need a 3 here. And then we essentially have the derivative right here, x squared. Any other power, it won't be undoing the chain rule, right? And the only power that would work is if that was cubed, because then you have essentially your derivative over here. So what did we do? We said we had to figure out which is f and which is g prime. So in this one, we made f equal to 4x, and it worked. And we made g prime equal to cosine, and that worked. And then here, we did the same thing. We let f be x squared, and g prime be e to the 3x, and it worked. Okay, but it just took two iterations, right? So what's happening? What's happening is we take the derivative when we set this f function to be the monomial. When we take the derivative of it, f prime, we get a lower power. That makes things easier. So then this f prime has a lower power of x and is giving us a chance for this to be an easier doable integral. And that happened both times. So f prime here was 2x. That got us closer. Then we had to do it a second time. And then that 2x will be constant, and then we'll have a doable integral the second time around. All right, so this is a very common technique when you have a monomial to a power times some other function like cosine or sine or e. It's often the case that you will make your f function be the monomial. That way, when you do f prime and you set up this one, that has a lower power, and it's doable or closer to being doable. Okay, so if we had, say, x cubed sine of x dx, what would we assign? What would we assign for f?
X cubed.
X cubed, right? And then how many iterations would it take us? How many nested problems will we have to do to work all the way to the solution then? So this just took one. We had x to the first. We got it on the first. We could just set up f equals 4x, g prime equals cosine x, solve the problem. Here was x squared, and we saw that like comes to two layers of undoing the product rule. Again, watch the video for that and make sure you understand that example. So if I have x cubed sine x, how many layers is that going to take?
Would it be 3?
Yeah, so for every power of x, you're going to have to do it. So like the first time, we'll make f equal x cubed, and then our f prime will be x squared. Then it'll be like this problem. And then we'll have to, make f x squared. And then we'll have to do it again. So so this would take like 3 layers. So f equals x cubed, but then we'll have 3 layers, or 3 iterations of undoing product. Okay? And so yes, so
do you mind showing those 3 layers?
oh no. Oh no. It would take half the class period. So
okay.
Watch this. So watch this problem I started this one last time, and then I gave the supplemental video to finish that problem, and you'll see what it's like doing 2 layers, and you'll say, no, I don't want to do 3 layers.
Okay, thank you.
It's a long problem, okay? So this would be the way you'd have to do it. but it'd be long. So now it's the right way, but it's not fun, right? Okay, so just kind of giving you the lay of the land here. So let's look at a different example then. How about, so any questions on that discussion about basically when you have a monomial to a power times like cosine or e to the something or some other function, we're going to let f be our monomial, and then that power on x is going to kind of determine how many iterations of undoing the product rule we'll have to do to get to the final answer. Again, watch this example from last Monday and the supplemental video.
I have a question.
Sure thing.
Isn't doing just U substitution easier? Like instead of the 3 layers.
You can't, so it won't work. So U substitution would kind of be like equivalent to like undoing the product rule, or undoing the quotient. Sorry, undoing chain rule. And this doesn't qualify for undoing the chain rule. So like, what do you want to make U equal to here?
So like, I guess we can let U equal x squared, and then it would be 2x, and then you would take the constant out of the integral.
Yeah.
And then I plug that in.
Yeah.
Oh.
It's not going to work. It's gonna get ugly. Your U integral will not be something simple. It'll just kind of keep being ugly like that, but in a different way. You might have something like a U in the denominator or something like that.
Okay.
So this doesn't really qualify for easy U substitution, just like it doesn't qualify for easy undoing the chain rule.
So we have to do this.
Yeah, this is the right technique for this one. Yep.
Okay. All right.
Yep.
Thank you.
Sure. Okay, so let's look at a new problem here, and we'll actually finish it out. So now I want to do natural log of x times x to the 5th. So what do we think? What's this going to entail? What's this going to take to do this, based on what we were just talking about?
AI, give it a shot.
Sure.
So f is going to be our x to the 5th.
Okay.
And it's going to be 5 layers of iteration.
Mm-hmm.
5 layers are iterations of undoing the product.
Yeah, exactly. So what do we got? We got about 40 minutes, and so that would be most of the class period. But let's just start the first step here and see what happens. F prime will be 5x to the 4th. And what's g?
1 over x.
1 over x, is that right?
I don't think it's 1 over x, because that would be the derivative. The derivative is ln x.
Right. So this is not, do you see that this is not correct? So what is 1 over x? 1 over x is the derivative of natural log of x. Okay? What function, if we take the derivative of it, gives us natural log of x? That's what we're asking here. Is there a function whose derivative is natural log of x, like from our rule sheet, like from our set of rules?
That'd be logarithms, right?
What's that?
Logarithms, right?
Well, no, the derivative of a log is not another log. Right? The derivative of a log is like 1 over the argument. So
A constant to the power of x.
A constant to the power of x. So that's an exponential function, right? And that also does not, the derivative of a to the x does not give a logarithmic function. It gives another, so it goes a to the x ln of a.
We don't know it yet.
Okay, so this is the point. We get to this little mini antiderivative problem that we need to do, and we don't know what that is, right? So this is kind of now saying, oh, maybe this was the wrong choice. Maybe this was the wrong choice. Let's try it the other way. Let's try, instead, let's make f natural log and make g prime x to the fifth. And let's just give it a shot. Now this is kind of different than what we've done before, but this is a different function, so maybe this works. So f prime now is, that's our 1 over x. G prime is, so g prime is x to the fifth, so antiderivative is?
1/6 x to the 6th.
Okay, so we're getting good at these now, right? 1/6 x to the 6th. So that's our setup work. So then, let me make this smaller here.
So Professor Ashbrook,
Yes,
while you're
please.
writing that out.
Yeah.
So would you say it's a very safe rule of thumb for it to be like, whatever you find taking the derivative is easier should be set to f, which is why we set that to monomials and not a safe, not a safe.
I don't, that wouldn't be like a hard and fast rule, but maybe a very loose guideline. I wouldn't say that every problem is going to be like that. So, I'd watch out for kind of making that generalization. So far, it seems like that's true. I just watch out for to get stuck in a rule that could have an exception.
So just stick to the whole f. Should be your monomials until proven otherwise.
Yeah. So often, again, it's like here we're seeing if this works, then here we're saying it's something else, right? So yeah. So it's just experience. Once you start doing, you have to do the homework, then you'll kind of see in what situations you're going to want to put what where. All right, so then this integral then would be g f prime d of x. So what's g? So 1/6 x to the 6th times f prime 1 over x. And then our f times g would be ln of x times 1/6 x to the 6th. So now, question. Did we end up with something easier, doable? What do we think? Is this, so I got x to the 6th over x. What can I do with that? Oh, please somebody know this. What can I do with x to the 6th over x?
Simplify it.
Yeah, 2.
X to the 6th.
So it's x to the 5th, right? Isn't that x to the 5th? Yeah, x to the 6th divided by x is x to the 5th. So, how do we do? Is it easier? Is it doable? Can we keep going? Yes, right? This is compared to, I'm doing the chain rule. This is very straightforward. So what is a? It's going to be 1/6 x to the 6th ln of x minus this, and antiderivative of this, which is 1/6 times another 1/6 x to the 6th plus c. So, did it take 4 iterations? Sorry, 5. Did it take 5 iterations of undoing the product rule?
No.
No, it just took 1. We're done, right? We got it. We got a very straightforward integral for our alternative integral from undoing the product rule, which had to just write down the antiderivative. And then we can, like we usually do, take fg minus the easier one. Okay, so this is different, right? We said, what did we say? We said that if you have, say, x to a power times a function, set the x to the power to be f, and your other function to be g prime, and then things will get easier because f prime will make the power of x less and less. Well, that's not the case when you have this. Natural log times x to a power is a different thing. It's a different animal. And you can do it in one iteration no matter what the power of x. We can make that the power 1,000 and do the same technique, and we'd be done with this many steps. Okay? So in this case, you set f to be natural log, g prime to be your monomial, then that derivative gives you 1 over x, which multiplies and this simplifies, and we got it in one step. Does it make sense? Did you see what happened?
Professor, can you re-clarify where you said it could take 1,000 times? Like, what did you mean by 1,000?
If it was x to 1,000,
It was X.
this problem there wouldn't be hardly any more writing on this page. If it were x to the 1,000 ln x dx, it would still be one iteration of undoing the product rule, and we'd be done. It doesn't matter what the power of x is when it's multiplied by natural log. It could be a negative exponent, a big positive exponent. When you follow this technique, it'll just take the one step, and we'd be done. Did that answer it?
Yeah, and then this technique of ours is where we don't set x to f.
Always, if you have natural log times the power of x, f is natural log. Because, and you'll find out quick, if you tried doing natural log here, then you won't be able to do the antiderivative of natural log.
Yeah.
And that will
So
remind
this
you. That will remind you, oh, this is where I have to switch it. This is where I do natural log of x is f, and my g prime is the power of x.
Okay, so this technique is where we identify that ln of x should be f, and the monomial should be g
Yep.
prime.
Right.
All right.
Okay.
I think I have a really dumb question.
Perfect.
I understand how we found A, but I'm not quite clear what A is.
The answer to the problem. This is the given integral. This is the given integral. This is the one we're trying to find the accumulation function for in closed form, so I'm calling that A for answer.
Okay, but it's the... If I was to call A something in terms of F or G, is there any way to say it in that way?
And it has nothing to do with F or G. I'm just using it as a symbol
Okay.
to mean the given problem.
Okay.
So this is
I'm
the
just
given.
Thinking of
This
it
is
weird.
yeah. This has nothing to do with F and G. This is I'm using the symbol A to stand for answer or to stand for the net accumulation function in open form that I'm trying to write in closed form.
Okay.
So it's not really a variable per se. It's kind of just like a label. Is that okay?
Yeah.
Yeah. So it's the given problem, the open form net accumulation function that our goal is to write in closed form.
Okay, that's what I...
Yeah.
Yeah, perfect. Thank you.
Uh-huh. Okay, any other questions on this one? So let's do one more of these. So we've seen, now we're starting to see like what kinds of problems are the common ones for undoing the product rule. And after we do this next one, we'll make kind of a summary list of the common forms that you're on the lookout for doing undoing the product rule. So we'll do one more here. And we're going to do arc cosine. Okay, so arc cosine. So if it's undoing the product rule, we're going to have an f and a g prime. Okay, so what should I make? So for sure, cosine inverse is going to be one of these. Which one should it be? Should it be f or g prime?
F.
Why f?
Because if you were to try to do the integral of arc cosine, it would be really ugly.
That's what we're trying to do.
Yeah, we can find out the integral for arc cosine.
Th-
That's probably why it should be F.
Right, so the point is, if I put it here, what do I have to do? I have to find the antiderivative of cosine inverse x to get this going, right? Well, that's what I'm trying to do. I'm trying to find the antiderivative of arc cosine. So I don't want to put it here, because this little problem here is the same as my original problem. Does that make sense?
Okay, sorry, just to clarify, so the reason why we're not putting it next to g prime is because we want to find out the antiderivative, and because we can't
That's what
find
this
out the
requires.
Right.
This
okay,
requires this is the antiderivative of cosine inverse.
Awesome. Okay, got it. Thank you.
But that's what we're trying to do, right? So this is like, we're like stuck, right? So that's why we put it here. And then what will we put for g prime then? What's multiplied by cosine inverse?
Oh, 1.
1, right? So there's nothing else. So what times cosine inverse is cosine inverse? 1. All right, so what is the derivative of cosine inverse? Do you remember? -1 over square root of?
1 minus x squared.
Okay, so there's our derivative of cosine inverse. Antiderivative of 1 is?
X.
X. So let's see if we got something easier here. That's the whole point, that this is doable. This one's easier. X times -1 over square root of 1 minus x squared. And then f times g will be x cosine inverse x. All right, how do we do? So we look at this and we say, given our known techniques of doing antiderivative, can we do that? Negative x over square root of 1 minus x squared. Is it doable, attainable? And all the experts who did their homework due this morning say,
Yes.
yes. What is it? How do we do that? Undoing the chain rule. Look, I've got a composite function. What's my power inside? So what's my derivative here? My derivative is -2x, which is essentially x. We got the right power, right? So this is, hopefully before I said it, you were thinking, oh yeah, that's undoing the chain rule. We can do it. Okay, so let's see, what will that be? We're going to do 1 minus x squared. And we're going to raise the power on this. What is the power on square root in the denominator? Well, that's -1/2. So then we're going to do 1/2. All right, now, so let's actually do the derivative for this one. So let's make that our first attempt. Okay, we know that's something close, right? We're going to do the derivative. Let's do the derivative instead of trying to eyeball all this here. There's kind of a lot going on. So we'll do the derivative, which is 1 over 2 times square root of 1 minus x squared times derivative of the inside, which is?
-2x.
-2x. Okay, so the 2's can go away. And I have -x over square root of 1 minus x squared. How does that compare to what we started with?
That works.
It is, right? It just is, right? We don't have to, we had no mess to clean up. We don't have to do any 2's or 1/2's here, because when we took the derivative, these 2's went away, and we had -x over square root of 1 minus x squared, which is exactly the rate function we started with. So this is right. This is it. So, I'll erase that.
I have a question
Yeah.
real quick. And it's not for this problem, but in general, like the integral of inverse tangent is like 1 over x squared plus 1, right?
The derivative.
So,
The derivative.
oh, okay. So if we were taking if we were taking the integral of something that was 1 over x squared, but it was plus, like, let's say 4, is that then not inverse tangent, or is that something else?
Plus 4 in the denominator instead of plus
Yeah.
1.
Yeah.
It is
4
inverse
instead of
tangent,
plus
but you
1.
have to do some trickery to it. You have to divide the top and bottom by 4, and you have to make it into a composite function. It is inverse tangent, but there's some algebra you have to do to
Okay.
kind of get it to do that.
Because I saw problems that were similar to it on the homework, and I was thinking, it just reminded me of it, and I wanted to ask.
Yep. If you couldn't work that out, then definitely bring that to office hours or email or something. Yeah.
Yeah, all right, thank you.
Okay. So now we're ready here. We got, so our open form is going to equal x times the f times g, x times cosine inverse, minus this antiderivative, which is our 1 minus x squared, and it's 1/2, let's just do square root over it like this, then plus c. Okay, questions on this example? Any questions on this one? Are we good? All right, so let's review the common forms. Of, let's see, what are the, so product, common forms, here we go. So let's review it. So we saw this, right? So x to a power times sine or cosine. These are the forms you're on the lookout for to say, oh yeah, I'm going to do undoing the product rule. Okay? All right, so we saw this. So the first one we did was x to the first times cosine. And then we did x squared times e to the x. So we said in these cases, you're going to make f equal to your x to the n. And then it's going to take n iterations to solve. Okay? That's what we said for these. Okay? And then natural log of x and a power times natural log of x. We said those were different. Those were different. We discovered that what do we want to make f here now?
You want to make f ln. Because
ln.
It's easier to do the derivative of that as opposed to its integral, which we don't think.
Yeah, so that again, making ln be g prime is kind of like it's repeating the question we're originally given. But making f natural log, everything falls out and we can do it in one step. One step. Okay? And then the last one we saw, I forgot to put it on here, is inverse trig functions. Is the other thing you're on the lookout for. If you just have your rate function is an inverse trig function, antiderivative of inverse trig, we just saw that this works very nicely for undoing the product rule. So there are other forms, there are other rate functions where this will work. But like 80% of the time, or 90% of the time, these are the ones you're going to come across. And so you're on the lookout for these forms to do undoing the product rule. So again, not to say that there aren't other forms where this technique works. There are. But these are the most prevalent. Okay, so questions on undoing the product rule. All right, we're going to move on to the next technique then. Which is rational functions. Okay, so if your rate function, so this is kind of closing this last chapter, starting a new chapter here. New chapter, rate of change function is a rational function. What is a rational function? It's the quotient of polynomials. So if you have one polynomial divided by another, that forms what's called a rational function. So I'm calling the numerator polynomial nx and the denominator polynomial dx. Those are both polynomials. What are polynomials again? Example. So that you always have whole number powers and any real coefficients. Okay, here's an example of a polynomial. All your powers of x are whole numbers. Your coefficients of those terms can be any real number. So we have one of these divided by another. So here, how about this? Is this an example of a rational function, that rate function?
Yep.
Definitely, right? So 2x squared is polynomial. X plus 1 is polynomial, real simple ones. So with this, with these rational functions, the first thing you look for is if the degree of the numerator, degree of n, is greater than or equal to the degree of d, you're going to begin by long dividing this fraction. And sometimes when you long divide, you'll get a new form that you can just do, and it won't require any new special technique. So let's do this. So we're going to long divide this. This means we're going to do x plus 1 So when you write out the numerator and the denominator, include all powers of x. So put 0 coefficients if you need to. So we got x to the first, constant, squared, x to the first, constant. So make sure you have a place for every power of x, even if you need to put zeros as coefficients. Okay, so just like you've done long division with just numbers, you do it the same way. So you say, we want to get 2x squared here. So it subtracts and goes away. What do I need to multiply by x to get 2x squared?
2x.
2x, I'm going to put that in the x to the first column. I'm going to keep that in my linear column here. So 2x times x is my 2x squared. That's what I wanted. And then 2x times 1 is 2x. And now I'm going to subtract. So I get my 0. That was the point. I'm going to get minus 2x. And then I'm going to bring down the 0, just like long division. Bring down the 0, and then we say, what do I need to multiply x by to get negative 2x?
Negative 2.
Negative 2, that's my constant. It goes in the constant column. Negative 2 times x is negative 2x. Minus 2. I'm going to subtract. I get 0, and then I get, let's see, minus a minus 2 is plus 2. Okay, so I got my quotient and my remainder, right? And so remember how you can write a fraction as quotient plus remainder over divisor. So this expression, this is a different way to write this rate function. By writing it as the quotient plus the remainder divided by the divisor. Okay, is this doable? Can we do this?
Yeah.
Very, right? X squared minus 2x plus 2 natural log absolute value x plus 1 plus c. Done. Closed form. So that's the closed form. It's the closed form for every net accumulation function that has this rate of change, right? Remember what the plus c is? It's the minus f of a. F of x minus f of a. That's our closed form for this open form net accumulation function. Any questions on this first example? Now sometimes you get, so this will always be n is greater than d, or n is less than d. Sometimes this won't be easy like this one was. And we'll need a new technique, that's what we're about to start now, is a new technique which it's called partial fractions, okay? But sometimes this will be just doable, but then sometimes it won't be, all right? So it won't be something smooth and easy like this.
I have a question.
Sure.
Could we have just split up the integral to begin with, like 2 over x plus 1 plus the integral of x squared over x plus 1?
So that was 4/7 equal to 4/3 plus 1.
Huh. Sorry. I was just wondering if we could split up the integral.
I know, I'm
right
answering your
again.
question.
Huh?
I'm answering your question. Is 4/7 equal to 4/3 plus 1? Because that's what you want to do here. So you want to with a sum, and then you want to break up the denominator.
No, the
Well,
numerator.
Mark, she was talking about splitting up the numerator.
Yeah,
Into what?
the integral of 2 over x plus 1 plus the integral of x squared over x plus 1.
Say it again.
Like we did in our homework.
Say it again. You want to
The
do?
integral of 2 over x plus 1 plus the integral of x squared over x plus 1.
Okay,
like we
but
did in
this
our
is equal
homework.
to 2 plus x squared over x plus 1. Not
Okay.
2x squared.
Okay, I see.
Yeah, this is different. That would be if it were 2 plus x squared.
Okay,
And then even so, this one we couldn't do. That's without something else.
okay.
Yeah. So that's I get what you're saying, but that's a different problem. Yeah, you need to split up a fraction. You need a sum in the numerator. Okay, so let's do another one here. So the first thing is check to see if the numerator and the denominator, if the numerator is greater than or equal to the denominator, long divide. And oftentimes that'll just do the trick. But sometimes this resulting fraction that you get where n is less than d, we need something more, and that's what we're going to do next here. We need something more. All right, so here's one. Here's a rational function. And we got one polynomial divided by another. And n is less than d, so we're not going to long divide. So first we ask, is it undoing the chain rule? Is it undoing the chain rule? Well, the derivative of this is what? 4x minus 1. Okay, so it's 4x minus 1. So is this right here, is this essentially the derivative of 4x minus 1?
No.
No, right? It doesn't match up. We can't multiply this by a constant multiple to get 5x plus 1. So undoing the chain rule is not going to work. Okay, so we need something else, right? And undoing the product rule, no, don't want to do that. So we need something new here. And what we're going to do is, if the denominator can be written as a product of factors, so can I write that as a product of factors? Meaning, can I factor this out? Does it work to factor it out? So we try 2x and x. And then I need to multiply to -1 so that it adds to -x. Can I do it? Remember the good old days of factoring polynomials?
So the first one can be x minus 1?
Let's try it. X minus 1 and this one plus 1?
Yeah.
So we'd have -x plus 2x. Is that equal to -x?
Should be the other way around.
Maybe the other way around? So try +1 here and -1 here. And that's okay. Trial and error is okay on these. So now x minus 2x. Does that give us -x? Yes.
Yeah.
We're good. Okay, so this is another way to write the rate function. And so remember when you add fractions, what do you need? You need a common denominator, right? So like if we had a fraction that had this as its denominator and another fraction that had this as its denominator and we were adding them together, this would be the common denominator, right? So we're kind of going to go backwards and kind of pull it apart. Rather than adding the fractions, we're going to see this as, hey, look, this is kind of like if we were adding fractions with denominators 2x plus 1 and x minus 1. When we would add those together, our common denominator would be the product of these two. The question is, what are the numerators, right? So what would the numerators of this be so that when we add these together, we get this correct numerator here? So we're going to approach our rate function as, so this is called decomposition. We're taking the single fraction and decomposing it into the sum of fractions called partial fractions. But we got to figure out what numerators we need so that when we add these together, we get exactly this fraction. Does it make sense? All right, so then we're going to add these together. We're going to add these together, work on it, and then that'll help us to determine what a and b are so that we get 5x plus 1 in the numerator. All right, so when we add these fractions, what do we do to the first one? Our common denominator we know is going to be 2x plus 1 times x minus 1. So what do we need to do to this first one to get the common denominator?
Multiply by x minus 1.
Yeah, so top and bottom, right? We can only multiply by 1 and not change the value. So we're going to multiply by top and bottom by x minus 1. Same thing here. I'm going to multiply the top and bottom here by 2x plus 1. Okay, the quiz is only one short question, so you're going to have plenty of time. I do want to finish this example, okay? So, all right, good so far? So what does that mean? So now we have our common denominator, x minus 2x plus 1, x minus 1. And then we can add the numerators. So a times x minus 1 plus b times 2x plus 1. So remember the good old day of adding fractions? So we got to do long division today, and now we get to do adding fractions. So what's the conclusion then? So then for these two to be equal, this right here, this numerator, has to equal what?
5x plus 1.
The numerator over here. Right. So we got to figure out what a and b need to be so that when we add all this stuff up, we get 5x plus 1. So here we go. So I'm going to do ax. I'm going to multiply this out now. Ax minus a plus 2bx plus b. So that's my numerators now. Has to equal 5x plus 1. So now we can match up the powers of x. So I've got a is a power of x, or is a coefficient of x, and 2b is a coefficient of x. And so those two added together have to equal 5. And then I got my constant terms, minus a, circle, and plus b. Those have to equal plus 1. So a plus 2b has to be 5. That's my coefficient of the... So when I add together these two, I need to have the resulting coefficient be 5. When I add together the constants, I need to have 1. So now I have what? A system of equations. 2 equations, 2 variables. You can solve that however you want. You can use elimination, substitution, a matrix method. There are many ways. Somewhere in your mathematical past, you solved systems of equations, and so you're going to apply that knowledge and use whatever technique you want. This one is all set up for elimination, right? So we can add these two equations together, and the a's will go away. So if I add these two equations together, I get 0 plus 3b equals 6, which means that b equals 2. And if b equals 2, then a equals, so you can just plug b equals 2 into either one of these, say this one, b equals 2, that makes 4. We need one more to get to 5. A equals 1. So then we got it. So we have the alternative form of this single fraction as partial fractions. So therefore my integral is integral of 1 over 2x plus 1, because I'm going to put my a here, plus 2 over x minus 1 dx. And that's 1/2 natural log 2x plus 1. Now we're ready to do the times 2 times natural log x minus 1 plus c. Closed form.